Thank you for taking the time to watch this design conference video for our capstone project. We are Group 20, otherwise known as Blue Sky Engineering, and we worked on a geohydronic surface heater for the runway application. I am Emma Hope, one of the co-team leads.
I'm Amy Funky, the other co-team lead.
I'm Gyewan Jung, I'm a assignment coordinator.
I'm Chris Keane, I'm the communications liaison.
Andre Godiger, project coordinator.
Tyler Rahal, assignment coordinator.
First, we would like to provide you with some background information on this project. The Rainbow Lake Airport, which we are focused on, is located in northern Alberta. This airport is known to become less accessible during the winter months due to accumulation of snow and ice on the airport runway. To address this concern, Blue Sky Engineering was asked to design a heating system to maintain the 30-meter by 1.5-kilometer runway at a surface temperature of 4 degrees Celsius by utilizing geothermal heating sources in the area. The approach we took was to design a hydronic heating system which would run underneath the airport runway. It should be noted that harnessing the geothermal energy from the source is out of scope, and instead our objective is to provide specifications for the working fluid at the inlet to our system for our client. There are 6 main design objectives of this project, both physical and hydronic. The physical design objectives are to determine the inlet diameter size and mass flow rate, as well as to create a module design that could be used in various future applications. The first hydronic design specification is that the system being designed must be able to maintain a surface temperature of 4 degrees Celsius for the runway. We also need to determine the best working fluid for this application and the temperature required at the inlet of our system. The inlet temperature can range from 60 degrees Celsius to 100 degrees Celsius from the geothermal source, which was a range provided to us by our client. There were a few design assumptions that we would like to outline before going into our design. The system was designed to withstand an ambient temperature of minus 45 degrees Celsius, with the lowest recorded temperature for that area being minus 44 degrees Celsius. However, through a climate analysis, we determined that the ambient temperature that should be used to size our system was minus 17 degrees Celsius. We also assumed that the heat loss downwards away from the runway surface would be 20% heat loss. Lastly, we assumed that the geothermal well will provide sufficient energy to power the system, as the heat exchanger design was out of scope for this project.
So the first part of our design was to look at the runway concrete structure and see how it would interact with the hydronic heating system. From literature, we knew that most hydronic systems use embedded piping that snakes and weaves underneath the surface, carrying the hot working fluid to then provide the thermal energy to the surface. Some key parameters with this then, as seen in the figure on the left, are the pipe depth, the pipe spacing, and the pipe diameter. Therefore, it's important to see what happens to the runway concrete structure when we embed some piping within them. To do this then, we started with a concrete design that looked at the loading conditions of the runway, which were specified by the client as a Boeing 737-300. Once we had the loading conditions, we produced some preliminary analyses on the runway structure to see what are the stresses like, what's the concrete slab thickness required, and what kind of stresses do the pipes experience. Based on these preliminary calculations, we were able to make some assumptions and conclude that the piping could be embedded within the concrete structure of the runway without many problems. However, further civil engineering design work will be required. Additionally, we looked at adding insulation underneath the runway surface, as was found in literature, to help promote the upward heat flux and help keep consistent with our assumption of 20% downward heat flux loss. Additionally, there's then also subbase beneath this runway structure to provide frost protection from codes and standards for Alberta runway pavement designs. Moving on then now to our design concepts, the main question that we had is, how are we going to embed these pipes into the runway surface to maximize the efficiency, reduce the cost, and just make this an overall sound and optimized design? To do this, then we came up with 3 design concepts. First was a straight pipe design. What this design has is a single supply line along one side of the runway and a return along the other, and then straight pipes that go across underneath the surface carrying the hot working fluid. The second design that we then looked at and came up with was the serpentine pipe design. What this has is one supply and one return on either side of the runway, effectively splitting it into 2, and then having our piping serpentine in and out of the runway before returning back to the return line. The third design concept that we then looked at was a spiral pipe design, in which the pipes go out into the runway, spiral around, and then return, weaving in on itself in a spiral, having effectively a hot and a cold pipe adjacent to one another, providing a very uniform heat flux to the surface. Overall, we had to balance and weigh these three design concepts in our design evaluation matrix based on complexity, cost, manufacturability, as well as how effective they were at delivering the heat flux to the surface. As a result, we came to the conclusion that concept 2 was the most suitable for our design application, and this is the one that we went forward with into our phase 3 calculations. So what does this design look like in practice then? Looking at our, we have single modules that are then stacked next to each other that span half the width of the runway and then go about 0.9 meters the other direction. These modules are stacked all along the length of the runway and carry the working fluid through the surface, through the structure, then heat the surface. These modules are made of PEX. This was also part of the design criteria to find the optimal pipe material. And the working fluid is ethylene glycol, which was also found to be the optimal working fluid. These modules are then connected to our supply and return lines through compression tees, and our supply and return lines themselves are made of stainless steel and use collection and distribution headers, which we size, as well as high-level fluid analysis to size the pumps, which will be addressed later on. For now, I'm going to pass it off to my colleagues. They're going to talk about how well does our system satisfy our clients' needs, and what are the results of some calculations and simulations in terms of heat flux and surface temperature.
A conjugate heat transfer simulation was prepared to analyze the temperature distribution above a single module, and a parametric study in which mass flow rate, pipe diameter, and pipe spacing was varied was carried out to optimize the pipe configuration underneath of the runway. In general, the temperature was observed to remain relatively constant along the 15-meter length of a module. However, it was observed to also vary across the width of the module. Despite the average surface temperature above a module remaining above 4 degrees Celsius, cold spots below 4 degrees Celsius were observed at the edges of the module between the 180-degree pipe ends. The cold spots occurring along the edges of the runway are considered to be insignificant as they do not affect the landing of an aircraft. However, the spots closer to the middle of the runway at the ends of the modules are easily solved by staggering the modules on either side of the runway by half of the pipe spacing. Based on this parametric study, the optimized system parameters are 1.5-inch NPS pipe diameter, 15 centimeter pipe spacing, and 0.2 kilograms per second mass flow rate. Figure 6 shows the simulated surface temperature distribution across the width of a single module. Neglecting the previously noted cold spots, the minimum temperature observed is only 5.65 degrees Celsius. Over the width of a module, the surface temperature has a linearly decreasing mean and oscillates between peaks above the heating pipe and troughs in the spaces between pipes. Note that the system assumes that an ambient air temperature just below 17 degrees Celsius is present, and in colder conditions, the system may struggle to completely melt snow and ice. Initial hand calculations estimated that a heat flux of 514 watts per meter squared would be required to melt snow and maintain a surface temperature of 4 degrees Celsius. This requirement is easily met in excess by our final module design, which achieves surface heat fluxes of up to 700 watts per meter squared and at a lowest point of 550 watts per meter squared. This element of oversizing adds to the robustness of the system, allowing it to remain functional under more extreme weather conditions than was initially conceptualized.
To get a full understanding of the scope of our work, Blue Sky Engineering was tasked with designing every single item inside the airport property line. So this includes our pump sizing and selection, supply and return line configuration, as well as the individual modules we've already gone through. Now, our system starts and ends at our mechanical building. Starting at the heat exchanger, our piping and working fluid go through our heat exchanger, then are followed by the air separator and expansion tanks, and that's where it enters our pumps. And these pumps are used to power that working fluid through the modules. Now, when our working fluid leaves the modules, that is when gravity is able to take over due to the 1% grade of our runway and return that working fluid to our sump tank. In addition, our sump tank is located a couple meters underground, which will help gravity to bring our working fluid back. Now, our mechanical building is located 170 meters north of our system. Now, this is due to requiring the building and any height to be outside of the airport fence line. From here, as the fluid leaves our mechanical building, the working fluid is able to go through the pump and onwards to our modules. Now here's an overview of our system. Starting at our mechanical building location, we have our supply line, which is an NPS 18-inch pipe, and then it goes along to our 6-inch pipe, and there's 14 sections of these, 7 per side, and this is where our pumps are located. Following these sections, we break down into 11 more sections, and these ones are 2.5-inch, and that will lead us to our modules. So each one of these 2.5-inch sections contain 22 modules each, and that's along the runway, which is shown in the middle. Just note that our render here is not to a full scale due to the total length of our runway. Now, based on this overall system, we found a head of just under 5,000 meters and a flow rate of 0.7 meters cubed per second. Now, to size pumps that meet this requirement, we will need 14, and those are again located on that 6-inch section. The pumps that we selected are the Gold's 3600 4x6-11 with the impeller diameter of 11.25 and motor of 125 horsepower to avoid to the point design.
So the expansion tank could also play an important role in this kind of closed-loop hydronic heating system because it maintains sufficient pressures in all parts of the system in order to prevent boiling, including cavitation at components. For the system, bladder-type expansion tank was chosen because it requires smaller volume and is reasonable price compared to other options. Expansion tank was sized based on formula and calculations given on ASHRAE handbook, and it was found that total expansion tank volume will be about 66.5 meter cubic. Therefore, 4 of Amtrak Extrural 15,000L and 1 of Extrural 10,000L were chosen to be installed.
Another important component of our project is the cost. The 3 major components of the cost were materials, devices, and the runway, which broke down into working fluid, choice of 60% ethylene glycol. Materials and the module supply line and return lines were PEX and 304 scheduled 40 stainless steel piping, respectively. Moreover, interfaces, flow, and control devices were sized and chosen as well. Lastly, to prevent heat loss to the runway surface, insulation was taken into consideration. Note, all parameters and components were quantified and shown on the far right column. The total cost of our system was $52.42 million estimate and did not include the installation cost as this was out of scope noted by our client. Notice on this graph, the supply and the return line being the largest cost due to materials being stainless steel and the mechanical house being located far away from the runway. The maintenance plan taken were 3 areas that would require regular maintenance, and that would be working components, the overall system, and the working fluid. For working components, which would include valves, pumps, and expansion tank, the heat exchanger to be designed would be in the future. These components would require yearly inspections, and a pressure indicator would be used to monitor the pressure drops. The general system would be the heat transferability, which is monitored using the temperature indicators, confirming that the snow and the ice is melting off of the runway, which will be replaced every 20 years as per airport standards. The working fluid, a 60% ethylene glycol solution, is replaced every 2 years and will be drained the fluid using the sump tank.
So returning to our initial design objectives, Blue Sky Engineering has presented a solution that uses an inlet pipe diameter of MPS 18 inches with a mass flow rate of 0.7 meter cubic per second. The modules are designed to cover an area of 50 meter by 0.9 meter and cover half the width of the runway. The minimum surface temperature is 5.65 degrees Celsius from a 60% ethyl glycol solution at 70 degrees Celsius. So for future work, to be able to install the heating system, a few items are required that were outside the scope of this project, and they include a structural analysis, installation plan, heating exchanger design, and the electrical system. And so we would like to give a brief acknowledgement to our client, Dr. David Nobbs and Dr. Jonathan Banks, and our advisor, Dr. Motara, and our course coordinator, Dr. Tetsu Nakashima. And here are the references for a couple of our images. On behalf of Blue Sky Engineering, thank you, everyone.
Sorry, I didn't see you there. Well, I guess I just want to take the time then to say thanks to everyone for an awesome Course 60 semester. I know it's tough and there were struggles along the way, but I had a really good time. Look forward to the summer. I hope you all find your beaches in aloha.